Have Luca Iliesiu, who will tell us about the evaporation history of charged black holes.
Great. Thank you very much for the invitation. It's been a very useful conference already for me. So today I'll be talking about the evaporation history of charged black holes. And this is work in progress that I think will come out very soon with Adam Brown, Jeff Pennington, and Misha Ushatyuk. Okay, so my work concerns a very, very simple, or at least at first sight, simple problem. Suppose that I have a Rise-to-Nordstrom black hole with mass m and charge q that doesn't have any matter around it. So I start at some point on this diagram and I let it evaporate. How does such a black hole behave? What's the evolution of this black hole along this plot as a function of time? And since this is a very old school problem that might seem boring at first sight, let me give you a little bit of a spoiler about why it's not boring. The reason why it's not boring is that when we start with a sufficiently large charge in flat space, even in our own universe, quantum gravity corrections are critical to describe the evaporation history of this black hole. And I'm not talking about a regime where the mass of the black hole has to become very small or anything like that. I mean even to describe the evaporation history of macroscopically large black holes, quantum gravity corrections will become important. And specifically for neutral particles, it turns out that perturbative effects will be important. So to describe how such black holes evaporate into photons and other particles, let's say. And for charged particles, namely particles that have the same charge as this charge, the charge of the black hole, it turns out that a combination of perturbative and non-perturbative effects are important, and these non-perturbative effects can be understood from a string equation. Now, the string equation has nothing to do with the string theory being a UV completion of the gravitational theory of the universe. It will simply be a mathematical technique to understand some of the non-perturbative corrections. Okay, so with this in mind, let's actually understand, give a back of the envelope calculation of why quantum gravity corrections are actually important to describe the evaporation history. And we'll see a little bit how this plot behaves like. So let's first discuss very briefly how neutral particles are radiated by black holes. So neutral particles drive black holes towards extremality because they don't carry away any charge. They only make the black hole lose some mass. And depending on the particle type, particles can have different gray body factors. And the way in which the black hole loses mass or loses energy as a function of time usually scales like the temperature of the black hole to some power. And I'll put exact numbers a little bit later in the talk. Now, let's compare this to charged particles. So when the mass of a charged particle is smaller than its charge in units of m Planck, this drives black holes away from extremality. And such particles, as in contrast to the neutral particles that I discussed earlier, get emitted through the slightly different process of Schwinger pair production compared to the neutral particles. So let's try to compare the decay rate of neutral particles to the decay rate into charged particles by simply using this formula for the Schwinger pair production that you can find on Wikipedia. This is the decay rate. And for where little m and little q we can take to be the mass and charge of the electron, and E is the electric field. Now, this is the formula for Schwinger pair production in a constant electric field. So we could say this is a good approximation in the region very close to the horizon of the black hole. And in the region very close to the horizon of the black hole, if you plug in what E is, E goes like 1 over the charge of the black hole. So overall, you get that charged particles, the decay rate into charged particle has this behavior. Now, ratio between the mass and charge of the electron is an extremely tiny number, famously. But if we make the black hole sufficiently charged, we see that the pair production of all charged particles is exponentially suppressed, while production of neutral particles is never exponentially suppressed. So this means that if we start with a very large charged black hole, this is actually, if you do the calculation right, you get that this black hole has to be bigger than 10 to the 6 solar masses in our own universe, if it were close to extremality. If you do that, then you find that this line just evolves downwards without actually moving sideways. So we're just driving the black hole more and more towards extremality. So this is what I said. The bound, if you plug in the numbers, is 10 to the 44 Coulomb charges. That corresponds to 10 to the 6 solar masses. So if you're to the right of this plot, you're just driving the black hole towards extremality. So in fact, the black hole, if we try to find the equilibrium point between these two processes.
Stupid question.
Yeah.
When you have Schwinger pair production, you can emit negative particles or positive particles.
Yeah.
Why don't you go up? Why don't you emit particles which uncharge the black hole and then you go the other way?
You do. So that's the point. Electrons, so here I'm assuming that, let's say, the black hole is negatively charged. So it would lose charge if it emitted electrons,
yes.
Right? So this is precisely the decay rate into electrons. So this is the only way it can lose charge.
Yes.
And the point is that this is so exponentially suppressed that if I start out to the right of this line, so this line is defined by this number in the exponent being order 1. So if I start out to the right of this line, I essentially don't produce any electrons, I only produce photons, and I can get very, very close to extremality until somehow these two guys equilibrate.
But I can also produce positrons, and if I produce positrons, those are going to be much more likely to be emitted, or no?
No. The positrons would be attracted back into the black hole.
Okay.
Yeah. That would be even further suppressed.
Okay.
Confused about the last point. When I look at your formula, you have capital Q divided by little q. If they have negative signs, then apparently you have an exponentially diverging.
Yeah, this is a formula that I think the formulas for Schwinger pair production assumes a relation between the sign of the electric field and the charge of the particle. So you should take this formula to only be correct for particles that have the same charge as the black hole, namely particles that get pushed away by the electric field of the black hole. Okay, any other questions? Okay, so if you look at the equilibrium rate between electrons and photons, you'll find that the black hole can get exponentially close to extremality if you just let it evaporate in a vacuum. So exponential in the charge of the black hole in 1/g Newton. Good. However, this calculation suffers from various problems for both neutral and charged radiation as we approach extremality. So let me start with the problem for neutral radiation. As we've become aware, or as we were aware since the 90s, there is a semi-classical breakdown of thermodynamics for black holes as they approach extremality. And this semi-classical breakdown can very simply be seen in the following plot, where I'll look at the energy above extremality for the black hole as a function of the temperature. But before I show how the black hole behaves, let's just remember that the energy emitted by a single Hawking quantum is proportional to the temperature. And while the energy that a black hole has above extremality is quadratic in the temperature. At some point, the energy above extremality that a black hole has becomes smaller than the energy that would be taken away by a single Hawking quantum. And this breaks the assumption that we typically make in thermodynamics, that we need an infinite number of quanta to be radiated in order to approach thermal equilibrium and not change the temperature. So the emission of even a single neutral particle seems to change the black hole drastically, and this is a problem. I'll just say that in a couple of slides, I'll explain how, by just looking at the partition function of the black holes, instead of at the Hawking radiation they emit, this problem seems to be ameliorated. So this is the problem for neutral particles. For charged particles, there's also a problem. Namely, the Schwinger pair production rate that you look up on Wikipedia gives you the production rate per unit time per unit volume. And the calculation that I did at some point should apply for black holes that are very close to extremality. And the near horizon region of an extremal black hole is ADS times ADS2 times S2, and this space has a divergent volume. So this suggests that the decay rate that I wrote previously should be multiplied if I want to compute the overall pair production rate per unit time instead of per unit time per unit volume to actually find what the number of electrons that reaches infinity is. I should multiply that by the previous answer by the volume of the space-time, so I seemingly get a divergence as the temperature goes to 0. So in principle, this could tell you that you could equilibrate the decay into neutral particles and the decay into charged particles at a much higher temperature that I computed before. The goal of the talk today will be to resolve these issues. Let me just say that we've made a lot of progress in understanding the thermodynamics of black holes in the past couple of years. The resolution for understanding the thermodynamic breakdown of near-extremal black holes comes from quantum gravity effects. And that's why I said at the beginning of the talk that quantum gravity effects will play a drastic role as we approach in the evolution of these black holes. So namely, in the work of Sen and collaborators, it was noticed that if we start out with an exactly extremal black hole that has an ADS2 times S2 near horizon geometry, there's an infinite set of zero modes that can deform this geometry that carry no weight in the Einstein-Hilbert action or Einstein-Maxwell action. So seemingly, the set of zero modes could lead to a divergence in the partition function at extremality. However, if I study now the black hole at a slightly non-zero finite temperature, the metric gets corrected, and what happens is that the zero modes that existed at extremality get lifted, and one finds a non-zero weight for all the zero modes that were present at t equals 0. Now, this weight is still very small as the temperature goes to 0, signaling the fact that these modes become very strongly coupled. So these modes of the metric that fluctuate can become very strongly coupled as the temperature of the black hole goes to 0, even though the black hole is macroscopically large. If you expand the Einstein-Maxwell action in the presence of these modes can be parametrized by these epsilons, which in turn parameterize the variation in the shape of the ADS2 boundary that is glued to the asymptotic region of the space-time. What you find is that the quadratic expansion of the Einstein-Maxwell action reproduces the quadratic expansion of the Schwarzian action. So essentially, the effective theory that describes these modes that are no longer zero modes is the Schwarzian theory. which at low temperatures becomes a strongly coupled theory, as can be seen from the fact that the quantum fluctuations of these modes is proportional to 1 over the temperature. Great. Luckily, the partition function of this theory can be exactly computed even in the regime of strong coupling, and one finds this new result for the partition function of a near-extremal black hole as the temperature is lowered, where the new element comes from the fact that what were previously zero modes at zero temperature, give you a large one-loop determinant in the partition function. So notice that the one-loop determinant gives you a power of temperature to the 3/2. So when the temperature becomes lower and lower, this quantum correction can drastically affect the partition function of the black hole. And this can be more clearly seen if we Laplace transform this partition function and look at the density of states of these black holes. So on the left, I've plotted the density of states of the black holes as I approach extremality. The dotted line is what you get if you only kept the semi-classical answer and you ignored the contribution of these zero modes. And you could see that the density of states goes to some constant value as the energy reaches extremality. However, when you include these quantum gravity corrections that become strongly coupled, the density of states goes to 0 as you approach extremality. And this is exactly what you would expect for an ordinary quantum system. Namely, the entropy decreases and goes to 0 as the temperature of the system also goes to 0. And this all occurs at a scale that goes like 1 over the charge of the black hole cubed. So it's a very small temperature above extremality that all these effects occur. Nevertheless, this scale is much, much higher than the scale that I found previously for equilibration between photons and electrons in our own universe. So if I'm interested in describing black holes in our own universe, I will go below this line if the computation that I presented earlier is to be trusted. From this density of states, you could also compute the average energy above extremality for a black hole. So here you can see how it was behaving previously, where it was growing quadratic in the temperature. And now at low temperatures, what you see is that it gets corrected by a linear term. And this linear term makes the average energy of the black hole above extremality be actually higher than the average energy of a Hawking quantum that it would emit. So seemingly this resolves the breakdown of thermodynamics. However, this is just a little bit of a cartoon, because in order to actually decide how this breakdown is fully resolved, we actually want to understand what the corrected emission spectrum for actual particles is, not just some statistical average where we don't couple the black hole to any fields. Okay, so to fully address the puzzle of the thermodynamic breakdown and address all the previous questions, we will answer the following. Number 1, how close do we truly get to extremality? Number 2, how is the spectrum of neutral radiation affected when we drive the black hole towards lower and lower temperatures? And number 3, how is the rate of charged particle pair production affected, once again, as we go towards this regime where quantum effects can become important? And from the answer to all these 3 questions, we will derive the full evaporation history of such black holes. Any questions? Okay.
Can we summarize this as saying that you want to understand the microscopics of that kind of plot? That you want to...
Not necessarily microscopics, but rather how the black holes behave when it's coupled to various sources. So I'm not specifically trying to, understanding the microscopics, I think most people would mean understanding how this coarse-grained plot becomes some discrete set of states. I just rather want to understand how the black hole actually behaves when it's coupled to matter. Yeah.
What is the value of rho of E when E is equal to E extremality?
0. Again, this is a coarse-grained plot. So this suggests that if this analysis is for non-supersymmetric black holes. So this suggests that in the absence of supersymmetry, there are no black holes as you approach extremality. So it's something very different than what, the typical semi-classical prediction, which tells you that there are E to the area number of black holes, where area is just pi q squared. Okay.
The factor of 3 halves in front of the linear term, is that universal or is that dependent on some things?
Yeah, it's universal in the sense that it doesn't depend on the, matter theory that you couple to, whether it's the standard model or some crazy theory, it would still be 3 halves.
Okay,
thanks. Maybe let me just say, the factor of 3 halves comes from the fact that in this set of, this will actually be important later in the talk, so let me say it now as well. In the set of modes that we have to integrate over, there are 3 that carry 0 weight that actually correspond to the SL2R isometries of the near horizon region. So because they correspond to the isometry, we technically should not integrate over these modes of the metric. These 3 modes don't technically change the space-time at all. So the factor of 3 halves just comes from the fact that when we compute the one-loop determinant of all these modes, there's this set of 3 modes that are excluded. And when you zeta function regularize the product of all one-loop determinants for all epsilon n's, you end up with this t to the 3 halves. Yeah, this will actually be important later in the talk.
Luca, maybe it's worth saying that there's an assumption that maybe it's worth saying that there's an assumption that there are no other, these are the only massless modes, which is generically the case.
Sorry, there's no assumption that there's no other massless fields.
No, I mean that
you
there's
mean
no other symmetry which is broken in the same sense, like supersymmetry.
Yes. That's why I said that the analysis here is for non-supersymmetric black holes in Einstein-Maxwell theory. If I have supersymmetric black holes, the spectrum of 0 modes, or the set of 0 modes that are relevant, is very different. And for instance, there at extremality, you'll find the density of states is exactly what you learn to love. That reproduces the count of Schrödinger and Waffe. So everything is consistent with what we've known from past calculations. Yeah. Yes, they do have 0 modes. The only difference with them is that here, so they would contribute factors of temperatures to some power in the grand canonical ensemble. So when you fixed the chemical potential at infinity. They turn out not to change this power when you fix the charge, when we're in the canonical ensemble in which we fix the charge of the black hole. So I just presented a slightly simplified picture here in which I ignored the 0 mode of the gauge fields because they don't contribute this power of t. They don't contribute to this power of t. Okay. Great. So I'll answer these 3 questions. So let me start with the evaporation of neutral particles. So to understand the evaporation of neutral particles, what we have to do is understand how a field is affected by the quantum fluctuations in the near horizon region. So what we could do in that regard is just take a field that we have coupled to gravity, let's say a scalar field, though I'll tell you about the generalization for the fields that actually exist in our own universe. So let's say we take a massless scalar field and send an incoming wave towards the black hole. And what we're interested is how the black hole reacts. So we're interested in studying the stimulated emission of this black hole in the presence of such a wave. So in order to do that, you have to see how this field is affected by the presence of these modes in the near horizon region. And what happens in the effective field theory that describes these modes is that these modes couple to the scalar that describes this field. So phi boundary of t is the value of the scalar of the propagating incoming wave on the boundary that separates the near horizon region from asymptotic infinity. And O of t, you could think about it as the scalar that's dual to this field phi that couples to the Schwarzian in the one-dimensional theory. Specifically, by doing the calculation of how an incoming wave propagates between infinity and the edge of the throat, you could explicitly write what the scalar field is at this boundary, where the parameter here, z boundary, is parameterizes where in the ADS2 region I cut off the space-time. So specifically, what I want to emphasize is that this value of phi naught behaves like this. It has r plus, which is approximately q, times the frequency of this mode to the power l plus 1, times r plus times this breakdown scale. Now, what I want you to remember is that omega and the breakdown scale are very, if I write their inverse in units of length, they're much, much smaller than r plus. So all these numbers are actually very tiny. So if I'm interested in a process of stimulated emission, and I look at Fermi's golden rule that is given in terms of the two-point function of the scalar that couples to the Schwarzian field in my effective field theory, these parameters that come from the gray body factors of the fields propagating between the edge of the throat and far away, and the region at asymptotic infinity, give the small parameters that allow you to actually study this problem in a perturbative expansion. Now, the nice thing is that in the Schwarzian theory, we can now completely evaluate what this two-point function of an arbitrary operator that's coupled to the boundary is even at very, very low energies, so energies close to the extremality. So here EI denotes the energy very close to extremality. Omega is the frequency of the incoming wave. And this product, this gamma function that actually denotes a product of four gamma functions with all possible alternating signs, actually comes from the two-point function in the Schwarzian theory. So this is the answer for what the stimulated emission is when I send an incoming wave. And from this, you could get what the spontaneous emission rate is. If I consider just a massless scalar, the majority of radiation comes from the S-wave sector of the scalar. The formula, if I want to write the energy flux for this massless scalar as a function of time, it can be written as this integral, where this factor comes from the gray body factor. This entire thing, you could view it as a Schwarzian corrected version of the Bose-Einstein distribution that typically emitted particles have as at arbitrary temperatures. So this exact formula, this formula should be exact up to arbitrarily low energy levels, should be compared with the formula for a QFT on a fixed background. So that should be applicable when the initial energy of the black hole is much larger than the breakdown scale, in which this entire distribution is just replaced by the Bose distribution. And you could actually see that if you take the limit when the initial energy of the black hole is much larger than E breakdown, this Schwarzian result actually becomes the Bose distribution, where the gray body factor appears in both. One important aspect, though, is that in the typical rate of Hawking radiation, this integral goes from 0 to infinity, so you could, in principle, radiate particles up to arbitrarily high energies, while here, there always exists some cutoff that's given by the energy of the black hole above extremality. And of course, the two-point function knows of that cutoff because it knows that the black hole cannot emit particles with an energy higher than the black hole has above extremality.
The final result, that's the one when the Schwarzian theory becomes classical.
Yes, and this is the standard answer in the literature.
So that's, you could, yeah.
Yeah. And you could see specifically how the spectrum of radiation looks like when you compare the Schwarzian corrected theory to the semi-classical answer, or the QFT and curved space-time answer in this plot, where here I'm sending the initial energy of the black hole to, let's say be 100 times 100 times above the breakdown scale. So these two plots look very similar to each other, almost indistinguishable. So this is what I call the semi-classical regime. However, in the quantum regime, where I, let's say, set the energy of the, just one second, where I, let's say, set the initial energy of the black hole to be 1/10 of the breakdown scale, the Schwarzian corrected answer and the semi-classical answers look completely different. And namely, you can see that previously the puzzle was that I was emitting particles that had too high of an energy, that took you below extremality. Now that puzzle is no longer there. I only emit particles in this very small window.
What is the dependence of G Newton in the Schwarzian corrected formula in the previous slide?
So the dependence on G Newton comes from this breakdown scale. So this breakdown scale goes like 1 over q cubed, or like m Planck over q cubed.
So it's a non-perturbative effect in G Newton.
No.
If I expand the quotients as an exponential, then the G Newton
at large energies, it is just like here. You would have, you wouldn't call this a non-perturbative effect, and you wouldn't call Hawking radiation a non-perturbative effect in G Newton, even though this is an exponential of something that goes like 1 over G Newton. But that's a good point. You expand this. Notice that at low temperatures, the sinh, the sinh of x is just approximately x. So actually, at very low temperatures, there's no longer any exponentials.
Trying to ask if it's a perturbative correction in G Newton or a non-perturbative correction in G Newton.
It's a perturbative correction. It's a perturbative correction to the gravitational path integral. Okay. So, as I said, in the quantum regime, the spectrum of Hawking radiation looks completely different. And we can characterize the total rate of emission by integrating all these plots. So for massless scalars, when I'm much above the breakdown scale, so the QFT and curved space-time answer goes like the initial energy squared. That's the typical flux. And when I find the contribution of quantum corrections, that changes to energy to the 7/2. So it's much smaller. You could do the same in the canonical ensemble. there is just some subtlety, which is the following: that at small, in the semi-classical limit, so when the temperature is much larger than the breakdown scale, the flux goes like T to the 4. At temperatures much below the breakdown scale, the flux now goes like T to the 7/2. The slight puzzle, or it's not actually a puzzle, or it's more a confusion that can be caused, is that the flux here in the microcanonical ensemble is seemingly reduced because 7/2 is bigger than 2. In the microcanonical ensemble, and it's seemingly enhanced in the canonical ensemble because 7/2 is smaller than 4. That small puzzle appears because the relationship between the microcanonical ensemble and the canonical ensemble changes. Precisely also because of these quantum corrections. Previously, the energy of a black hole above extremality behaves like temperature to the temperature squared. Now it behaves like the temperature, and that's why the power here and power here agree, while the power here and the power here disagree. It's just because the relationship between the two ensembles is also modified as the temperature is lowered. So this all includes all gray body factors. We repeated the calculations, and the gray body factors that we derived actually agreed with the previous gray body factors derived in the literature, and they were important. The gray body factors, to get all these numbers and to get the powers right, these gray body factors are actually important. Now, we don't have a massless scalar, as far as we know, in our own universe. We have photons and gravitons. So one, in principle, should also compute the flux that a black hole emits into photons. It turns out that in the photon and graviton sector, there is a slight complication because there's mixing between the photon modes and the graviton modes. Even the lightest photon mode is mixed with the graviton. But nevertheless, with some hard work and some really good postdocs, you could do the calculation, and you find again that the flux is lowered for photons. Instead of going like the initial energy to the 5th, it goes like the initial energy to the 11/2. It's actually not lowered for gravitons. And that's a slightly more subtle, confusing effect that I won't discuss for now, but the point is that semi-classically, the dominant channel in our world at higher temperatures is equally divided between photons and gravitons, but the dominant evaporation channel in our world for at low temperatures is actually dominated purely by photons, because the quantum corrections modify the flux of photons slightly different than the flux of gravitons. This has to do with the fact that the effective scaling dimensions of photons and gravitons in ADS2 are different. Okay, so this is the answer for neutral particles. The law is corrected, but it's still a power law in the temperature or in the initial energy of the black holes. So we've resolved the puzzle of the breakdown of thermodynamics, but seemingly we can still get close to extremality by emitting, through the fact that we're not emitting charged particles. So now let's understand how the evaporation into charged particles behaves.
So which
yes?
one was less than small energies and how?
Which one is between photons and gravitons?
What are the first two ones?
Oh, it's because in this plot I didn't have enough space. So second one is always quantum. First one is semi-classical. So semi-classical, the photon and graviton have the same parametric scaling with the initial energy. But once I go into the quantum regime, the photons become more important. Okay. Good. Okay, so given that we now understand neutral particles, let's discuss the evaporation into charged particles. So let's again look at the case in which we're close to extremality. So the Schwinger pair production rate can be computed by going to Euclidean signature. So we're in ADS2 cross and Euclidean ADS2 cross S2, and finding instanton configurations of charged particles and computing the new partition function. So the type of instanton configurations that are relevant in ADS2 times S2, the solution to what happens when I put a world line of a particle in an electric field in ADS2 is just the world line becomes a circle of constant radius when the particle has a mass less than its charge. So this is just a standard classical mechanics problem for how charged particles behave in a hyperbolic space that was solved in the 80s. However, there's a problem, which is that this instanton can be anywhere in ADS2. And that's precisely where the divergence corresponding to the volume of the space-time came in gamma. That was the question that I posed at the beginning. And we can also see this at the level of the Schwarzian theory. These modes where the fact that the instanton can be anywhere inside ADS2 means that there's a set of two zero modes, two translations within ADS2 that seem to exist. And the question is, do these translational modes get lifted? So translations of this instanton in ADS2 are generated by two of the free generators of the typical SL2R isometry of ADS2. So if I include corrections, if I now try to do what I was doing before and look at fluctuations of the boundary metric, the two modes that I previously wasn't integrating over because they were part of an SL2R isometry are now broken by the presence of the instanton. And now in principle, I do have to integrate over them. So the two modes of the Schwarzian that correspond to these translations of this instanton are the n equals 1 and -1 zero modes. And you could see that these have exactly zero weight if I don't take into account the back reaction of the instanton on the space-time. So in principle, the integral over these two modes gives you the divergence that reproduces the divergence in the volume of the space-time. So this tells us that perhaps we should try to find how these modes back react on the space-time in order to see whether or not these two translational modes get lifted. And what it turns out is that including the back reaction of the particles and the space-time will give weights to these modes and affect the Schwarzian perturbation theory that I'm talking about. So to see how the instanton affects the space-time, you could write down the entire action of the space-time as your initial Einstein-Maxwell action plus the action of the world line of this instanton in an S-wave sector. The point is that while previously your solution had the black hole to be identical on the outside of the instanton and on the inside of the instanton, when now you're looking at a back-reacted solution, you can consider a black hole solution that's different outside of the instanton than one that's considered inside the instanton. Due to the fact that this world line has some non-trivial stress tensor that can lead to a non-trivial gluing between these two black hole solutions. So in total, my solution that has that's a composite of two different black hole solutions will have free total temperatures that are useful to keep in mind. The first one is suppose that my space-time has an asymptotic mass m and the charge q. There's the temperature that corresponds to the standard T Reinster-Nordstrom with respect to this m and this q. There's another temperature that corresponds to the actual temperature of the space-time when the mass of the exterior solution is m and its charge is q. And finally, there is a temperature that identifies the periodicity of the thermal circle on the inside of the instanton, which now has mass m bar and charge q bar, where q bar is just big Q minus little q. The important point here is that, that will become apparent in 1 second, is that if I continue the space-time on the outside, the one that has mass m and charge q, past where the instanton is located, I no longer get a smooth geometry, because I don't have to actually impose the standard smoothness condition with respect to this black hole. I only have to impose it with respect to the black hole of mass m bar and charge q bar. This small difference causes an effective defect to appear when you continue the geometry from the outside past the instanton. Now, I want to emphasize that this defect is nowhere to be seen in the actual geometry. It will just serve as a mathematical tool to parameterize how big the back reaction of the instanton is on the space-time. And these defects will actually be very similar to the defects that Eric talked about this morning in the context of the Maxfield-Turiachi paper. So even when including this back reaction, the instanton solution can be found analytically for any m and q. And here are some of its properties. The first property is that the instanton size is actually very, very tiny. The smaller the temperature of the black hole, the smaller the ratio between the area of the instanton measured in ADS2 units. So as I go towards the extremality, the instanton keeps shrinking and shrinking. The second point is that in our own universe, where the ratio between little m and little q is very small, the effective defect angle seen from the outside of the geometry, so this guy, which captures the difference between the inverse temperature of the actual geometry versus the inverse temperature of a Reissner-Nordstrom geometry with the same mass and charge, this defect angle is very small. And of course, that should be the case because electrons have very small back reaction. So that kind of makes sense. The third property, and this is something that I found quite surprising, but a posteriori it makes sense, is that the mass of the black hole after the instanton is emitted is actually much closer, it's actually above the breakdown scale of a black hole with the new charge. So q minus little q is what q bar is. So essentially what this is telling us is after we emit a single electron, the black hole goes way out of the region where thermodynamics could break down. And this m bar can also be used to compute the velocity that an electron has when it goes to the asymptotic boundary. And one finds that actually the velocity of this electron is absolutely gigantic. Namely, the relativistic factor is little q over little m, which is 10 to the 22. So the relativistic mass of the electron when it gets expelled from the black hole is q times m Planck. So it has an actual energy that's pretty close to the Planck scale. This is quite surprising because in many old calculations to compute how far this mass of the electron tells you how far a black hole is taken away from extremality by the emission of an electron. And the fact that the electron is so relativistic actually means that it's taken away very little above extremality, much less than you would naively expect. And finally, you can compute the actual on-shell action of this instanton. And what you find is actually a very nice answer, is that it's given by the area of the new black hole plus the temperature weighting corresponding to the new black hole. Yeah, and maybe let me just say, this is actually approximately the old black hole action plus the action of the instanton that doesn't back react. So the effect of the back reaction is actually not that large on the on-shell action. Let me come to the most important role that the back reaction plays, namely how the translational zero modes now get lifted. So in the presence of these corrections to the extremal metric, we can now again see what happens to the zero modes, but now look at the configurations where the instantons back reacts on the metric. And while previously in the Schwarzian, in the quadratic expansion of the Einstein-Maxwell action, here you encountered a term that went like n squared times n squared minus 1, that gave you a set that made the modes n equals 1 and minus 1 exact zero modes. Now, the fact that I have a defect angle that appears to be there from the outside of the instanton lifts the n equal 1 and minus 1 zero modes by a very small amount. So we have a very, very light set of modes that correspond to the translation of the instanton within the ADS2 region. And you can again compute the path integral in the presence of these near zero modes. And what you find is two contributions. One comes from the one loop determinant of the particle in the ADS2 geometry multiplied by e to the minus on-shell action of the instanton. There's an I because there is a set of unstable modes in Euclidean signature, which signifies the fact that this instanton actually gets emitted. Sorry, the pair production actually occurs when you go to Lorentzian signature. But the more important elements is that there is a one loop determinant, which now instead of going like temperature to the 3/2, goes like temperature to the 1/2. So now you could actually compare this result with what you would expect to get from pair production. So from pair production, when you only include one instanton, you should be able to capture the fact that the ratio of the solution in the presence of the instanton divided by the partition function of the system in the absence of instantons goes like the first order in the expansion of e to the I gamma b. So this should go like 1 plus I beta gamma. And taking the ratio between this and the actual black hole partition function gives you exactly the right answer, precisely because Z black hole has a factor of 1 over beta to the 3/2, corresponding to the free SL2R modes, versus 1 over beta to the 1/2 that appears because two of the modes are now getting lifted. So from this, we can actually find out what gamma is, and we actually get a finite answer where there's no longer a divergence associated to the size of ADS2. Essentially, that divergence was cured by the fact that two of the modes of the Schwarzian get lifted again. So this is the answer, where e to the minus I instanton effective is this term in the parenthesis. Now, there's a final question. To fully compute gamma, we need to understand how to sum over all instantons to produce this factor of e to the I gamma b. Here we only produce the term in the linear expansion. In principle, this automatically happens. The fact that all the instanton resum to e to the I gamma b automatically happens in the dilute gas approximation, where you assume that the instantons don't interact. However, given that a single instanton was, that even for a single instanton we had to consider the back reaction of the instanton of the metric, how does the dilute gas approximation actually work when you include this back reaction at the level of the gravitational path integral? And it turns out that a way to resum this gas of instantons is by noticing that the moduli space of instantons on this geometry is the same as the moduli space of conical defects in this near horizon geometry. And the moduli space of conical defects was actually very much studied in the context of hyperbolic geometry in the same paper that Eric mentioned this morning. So in principle, to compute the partition function with all instantons inserted, one has to resum the partition function for every k with k defects inserted. Now, if the dilute gas approximation is to actually hold, we should find that this zk defect behaves like temperature to the power k, 1 over temperature to the power k, times the old black hole times the old black hole partition function. Now, that turns out not to be exactly the case, it's only approximately the case. So it turns out that to understand the moduli space of these conical defects, it's actually useful to relate the path integral over this moduli space to a certain deformation of the large p 2 comma p minimal string, which turns out to be dual to the integral over this moduli space. I unfortunately don't have time to go into the details of this, but this deformation modifies the density of states in the theory in a way where we can now extract what the new gamma is when we resum over all instantons. This gamma just appears through a shift in the edge of the spectrum, which is the same shift that Eric also discussed this morning. The imaginary part of the shift gives gamma. The real part of the shift gives the change in the extremality bound. And it turns out we can compute gamma systematically by looking at this shift, and to leading order, we find exactly what one would expect from a dilute gas approximation, but only morally, because the dilute gas approximation also includes the volume of the space-time to a correct power. Here we're getting the dilute gas approximation without including the volume of ADS2. We get a regularized version of this approximation. Somehow everything miraculously works to give us the same finite value of gamma that we were finding previously. And one, in principle, finds subleading corrections to this that can be systematically computed. They're subleading in the on-shell action of the instantons. And there are also corrections to the shape of the entire density of states that is also subleading. So with all these calculations, with this new gamma, we can compute the evaporation. I can tell you what the evaporation history of a charged black hole actually is. So suppose we start at a very large mass, much above the range of 10 to the 5 solar masses, that is shown here, or 10 to the 44 coulombs. So initially, the black hole just approaches extremality and goes well below the extremality region. So this is the dotted line is the region where the black hole becomes near extremal. The dashed line is the region where the thermodynamics is expected to break down. So initially, Hawking radiation has this behavior, and the mass of the black hole goes like a power law in T with the power to the 1/4. That gets corrected by Schwarzian corrections as I approach extremality, and eventually, when I get exponentially close to the extremality in the action of the instanton, I emit 1 electron. Now, this keeps occurring a couple of times. So, you emit 1 electron, you go away from extremality, well above this breakdown scale. Then again, you decay all the way down to extremality. It repeats a couple of times until eventually you get to the point where Schwinger pair production is no longer exponentially suppressed. And you quickly go away from extremality towards 0 charge. And eventually, you just end up with a Schwarzschild black hole that just evaporates for neutral radiation up to the point where it goes to zero mass. And these timescales between different between the production of different electrons is huge. Okay, so to summarize, charged black holes with large enough charge get incredibly close to extremality when left to evaporate in vacuum. Close to extremality quantum corrections drastically affect the Hawking radiation for neutral and charged particles, but we can now systematically compute everything and predict what an observer far away from the black hole would see, even in this very quantum regime. So finally, it would be nice to understand a bit more what the connection between this calculation is and the weak gravity conjecture. It seems that having no charged matter doesn't seem to cause any problem in perturbation theory, but perhaps if we look at some non-perturbative processes, we'll see that the weak gravity conjecture has to be satisfied. It would also be nice to repeat this calculation for BPS black holes, where we now have a big gap in the spectrum, and we expect that the spectrum of neutral radiation should exhibit this gap. Namely, an observer from infinity should see spectral lines, like you see for the atoms in our own world, that are characterized by the scale of this gap. And finally, people have also recently studied how quantum corrections play a role in Kerr, and it would be interesting to study what the pair production for near extremal Kerr is, and whether that has any connection to the process of superradiance. I'll leave it at that. Thank you.
Thanks a lot for the very nice talk with some nice figures here. Time for one question, let's say.
Okay, thank you. That was very interesting talk. I just have a small question. In this domain where your effects are interesting, very quantum, if I had to look at the rough macroscopic way of thinking about this, let's say in the Strominger-Waffa model or something like that, this is the case where I have only one or two non-BPS excitations over the extremal hole?
Yes, but that picture is wrong for non-supersymmetric black holes. Even for supersymmetric black holes, the case where you only have one or two excitations is somewhat misleading, because right above the scale where you have a gap in the spectrum, so this is how the spectrum for near BPS Strominger-Waffa black hole would look like. So right above this gap, there's a continuum of states that gets very quickly populated. So I think there were previous string theory computations done in the past that tried to extrapolate what the spectrum of these black holes looks above, above the BPS bound, and they saw a mode that lived, very close, actually at exactly this value of the gap scale that we also found using the gravitational path integral, but people don't see a continuum of states. And that's because typically the calculations are only done at weak coupling and are extrapolated to strong coupling without necessarily knowing whether in a correct regime of validity. Maybe a closer calculation is the one presented this morning, in which there was a plot at one loop order in lambda in the context of n equal 4 super Yang-Mills that seemed to exhibit the same type of gap as what I'm showing here.
Okay, thank you.
Well, if there's another burning question, we can ask it, but otherwise maybe we can take a break before the discussion. So, all right, let's thank Luca again.